Thank you very much. It's really a privilege to be able to talk to this group about Watson and the Jeopardy challenge, which, frankly, 5 years ago was just a really cool idea that a dozen of us thought would be kind of fun to explore. And ultimately, it has evolved into quite a public phenomenon for IBM. And so what I'd like to do is give you a little introduction to Watson and some insight into how the investment that NITRD and its member agencies has laid the foundation for the technologies and the people that really made Watson possible. And so let me start by answering a question that we're commonly asked, which is, did you design Watson by trying to model the brain, or does Watson think like humans? And quite simply, the answer is no. And let me give you an example. So this morning, while I was sitting listening to Shrutak Patel talk about sensors and, in particular, the analog brake system, he mentioned that typically it's something that works transparently with occasional feedback to the human, especially if it's not working. And so in my brain, this actually triggered a connection with a problem my father had with his car and his analog brake system. It started to have a problem, and the feedback was on the dashboard, a little red light came on saying you have a problem with your analog brake system. And so this ended up being a rather expensive repair, and my father actually has a PhD from Stanford in plasma physics. So he's an electrical engineer, mechanical engineer, has experience in optics, and decided to fix it himself. And so he did this by taking some black electrical tape, cutting out a neat little square and placing it over the light on the dashboard so that he wouldn't have to look at it anymore. And thinking about that and the fact that he'd gone to Stanford reminded me that when he was at Stanford, he actually went on an NSF fellowship. And having, I think, that funding maybe gave him a little more free time, gave my parents a little more free time. And I was born while they were at Stanford, and born at the Stanford Hospital. So arguably, the National Science Foundation can take some credit for my existence. And so now there's 2 points to that story. So one is investment in people is really a key part of this. And the investment is not always as personal as it might be with me, but as I'll show, it's investment in training the talented and educated people that are going to create technology and continue to apply it. So the second point I'll talk about is the technology itself and how all of these different areas can come together to create a system like Watson. And then the third point I want to make is the need for data, which has been mentioned, and really all three of these topics have been covered today. But data in particular when it comes to evaluating systems both at the component level and at the end-to-end level, and the use of data for training these kinds of systems when you're using machine learning. So fortunately, Kevin Knight already made a great case for the challenges in understanding natural language and building computer systems that can do that. So we typically make this point by comparing the problem of doing question answering to something like chess. And chess was another grand challenge problem that in the 90s, nobody thought you could build a computer system that could play chess at the level of a grand champion. But ultimately, that's a relatively straightforward problem to model with a computer. Contrast that with human language, and the point has really already been made quite well that that's a big challenge. And so here's another example. If data is represented in a very structured way with explicit semantics, it's actually easy for a computer to use that and produce answers. So if I want to know where Einstein was born, if I have a table of people and their birthplaces, I can easily pull out Einstein as the correct answer. But what if I want to answer that same question using natural language, and I have this paragraph? One day, from among his city views of Ulm, Otto chose a watercolor to send to Albert Einstein as a remembrance of Einstein's birthplace. So now that text contains that same information, or at least it suggests that it contains the same information. But even for a human, it's somewhat difficult to pick out the answer of where Einstein was born. And just imagine how hard it is for a computer. So one more example, if I want to know who ran GE and I have a table with organizations and people that ran them, I can pull out Jack Welch. But if I had this sentence, if leadership is an art, then surely Jack Welch has proved himself a master painter during his tenure at GE. So from this, I guess we could at least infer that Jack Welch was a painter at GE. But you know, as humans, understanding the meaning of that, the implicit meaning is that really he was the leader of that organization. And so it's this challenge of understanding natural language that brings us to the Jeopardy challenge. And ultimately what we were interested in was tackling natural language by building an open domain question answering system. But question answering has been a problem that's been researched for quite some time. In fact, you can go back to 1970 to find a survey paper on the state of the art in question answering technology. I think it's Simmons in the computer CACM. So IBM decided to elevate this to a grand challenge problem and really invest in it and see what we could do. And to do that, we want to have some public way of demonstrating this as a grand challenge problem. And this is where Jeopardy comes into play. So Jeopardy actually has 5 key elements to it that really make it worthy of driving this technology. So first, it covers this broad open domain of problems. So let me give you a few examples, real Jeopardy questions. If you're standing, it's the direction you should look to check out the wainscoting. This is the interactive part of the presentation. Anyone? Down. So the wainscoting is down, although the correct response in Jeopardy format would be, what is down? Thank you. So you get right in single Jeopardy. So for $600 in cell division, mitosis splits the nucleus and cytokinesis splits this liquid cushioning the nucleus. What is a cytoplasm? The first person mentioned by name in The Man in the Iron Mask is this hero of a previous book by the same author. D'Artagnan. This is a tricky one, so that's quite good. And then of the 4 countries in the world that the U.S. does not have diplomatic relations with, the one that's farthest north. What is North Korea? And so just from these 4 sample questions, you see we're asking for directions, we're asking for heroes, we're asking for liquids, and we're asking for countries. And so it's covering a broad range of topics expressed using complex language. The answers require precision, so it's not good enough to just search the web and return a hit list of web pages or even the top web page. Even if you assure Alex Trebek that the answer is in there, you must come up with a precise answer, and you have to have confidence because, again, there's reward for getting it right, but penalty for getting it wrong, and you have to do all of this quickly. So when you examine the Jeopardy task in more detail, those 4 clues give you 4 different kinds of things Jeopardy asks about. But in fact, when we sampled 20,000 Jeopardy questions, we came up with 2,500 different kinds of things Jeopardy asks about. And so this is a distribution of how frequently those different kinds of things occur. And so you have common topics like films or groups or capitals or songs. But even the most frequently asked about topics represent a tiny fraction of all the data. So if you're going to go about solving this problem, an approach that uses databases or structured information ultimately is not going to scale because Jeopardy will come up with a question about anything. And this was an interesting aspect of the problem. In particular, there are some questions that don't even describe a type or the kind of the correct answer. So let me give you an example. From the category Lincoln Blogs, Treasury Secretary Chase just submitted this to me for the 3rd time. Guess what, pal? This time I'm accepting it. What is his resignation? And in a D.C. crowd, I often get that response very quickly because well, either you know your Civil War era history and you just know that Chase submitted his resignation 3 times before Lincoln accepted it, or you're somewhat cynical, and what do secretaries submit to their presidents? It could be a bill, it could be a speech, most likely a resignation. Now, I was presenting this to some middle school students and posed this same question, and actually didn't expect anybody to know the answer, but one girl in 6th grade raised her hand, and her response was, what is a friend request? And I thought, now I'm sure that if Lincoln had Facebook back in 1860, he would have been friends with Chase, at least until he submitted his resignation. But what's interesting about this example is, again, it talks about the challenges of understanding natural language and how its usage is so context-dependent and associated with your experience and your paradigm. And so for older, cynical people, resignation, something that's submitted or accepted might be a resignation. But for a middle school student who's steeped in social media, it's clearly a friend request. And so how do we go about discovering these automatic relations? And so just at a very quick summary here, we're applying a variety of technologies to automatically extract relationships from text. And by applying things like parsing, and by parsing I really mean parsing like you learned in 8th grade grammar, but writing a computer program that can do the parsing to extract relations between things, we can automatically discover things like inventors patent inventions or officials submit resignations. And I don't mean this to be exclusive. There are other things officials could submit as well, of course. People earn degrees at schools. Fluid is a liquid or liquid is a fluid, and all automatically extracted from text. And then we can use what we've learned to apply that and try and solve the problem. And so rather than go through this example, I want to jump to another example here. In May 1898, Portugal celebrated the 400th anniversary of this explorer's arrival in India, Vasco da Gama. And so a computer system is going to go about solving that by breaking it down into keywords, possibly parsing it into a predicate argument structure, and we might search our content to find a possible match. Using keyword search, we find this passage: in May, Gary arrived in India after he celebrated his anniversary in Portugal. So actually, the correct answer is Gary. And we know that because we have very good keyword match, right? Anniversary, Portugal, May, celebrated. Point being that keyword match alone can lead you astray and provide evidence for the wrong answer. Here's a passage with the correct answer. On the 27th of May, 1498, Vasco da Gama landed in Capet Beach. Now, the problem here is that it only has one keyword in common with the original question, and that word is May, which is a month, and it's also an auxiliary verb and doesn't have a lot of meaning. So we need to apply deeper analytics to analyze that passage as evidence to support Vasco da Gama. So we can use temporal reasoning to know that if in 1898 we're celebrating the 400th anniversary of something, that something occurred in 1498. We can use statistical paraphrasing or techniques to know when two things mean the same, to know that landed in can mean the same as arrived in, and we have a match. And geospatial reasoning to know that Capet Beach is in Kerala and Kerala is in India, and so again we have a match. And so now by applying deeper analytics, we can evaluate this passage as evidence for the correct answer. And we plug all of that into this high-level architecture shown here, with a question coming in and an answer coming out at the right. And all I really want to say about this is how there are a number of technologies that get plugged into this architecture to make the whole thing work. Natural language processing, information retrieval, knowledge representation and reasoning, machine learning, and parallel and distributed computing. All areas that NITRD and its member agencies have invested in over the last 20 years, and which feed into our ability to integrate all of these things together into an end-to-end system and solve a very interesting and challenging problem. Now, coming to the people aspect of it, this is a picture of the team that built the system. And again, the point here being that this team is all educated at different universities. All these universities benefit from funding from, again, these same agencies. And this is really the starting point for making something like this possible. The end point is shown here, where Watson competed against Ken Jennings and Brad Rutter and ultimately was victorious. And perhaps most importantly, in the final Jeopardy round here, Ken Jennings, knowing that he was not going to win, added an additional comment which says, "I, for one, accept our new computer overlords." That's what's written in that tiny print there. So I appreciate his sense of humor, but I think he's a little overly optimistic. And while I'd like to think we're there, we're nowhere near there. And in fact, there's an awful lot of work to be done to continue to advance the technology. And these are just some of the areas that we're exploring: healthcare, tech support, enterprise knowledge management, government. And there's just a lot of work left to be done. And so continued investment is just absolutely essential to leverage this technology. Thank you.
Can you say a few words about the economic implications of this? What kinds of industries will be affected? What professions? And I'm sure you've made a lot of money on Jeopardy, but you probably have other plans as well.
Well, unfortunately, in the case of Jeopardy, none of the winnings went to the team members that built the system. But that aside, people often ask, is the intention that this technology would replace humans? And a point that I want to emphasize is that this question answering technology is really a decision support system, and it's supporting humans. And so the idea is to allow humans to make better decisions by giving them easier access to much larger volumes of information, analyzing that information, and making it more readily accessible to them. And so one specific example that we're currently exploring is how to apply this in healthcare and create a differential diagnosis system to support physicians or healthcare providers. And physicians can't have access to all the latest research and even access to a patient's medical record, which can be enormous. And a system like Watson can provide much better access to that information, analyze it, connect a bunch of different pieces together, and then present it in a way that it can be more consumable to the ultimate decision maker, which is the physician. And a key part of that is then easy access to the evidence that supports that decision and the reasoning process that went into it to come to those conclusions.
So say a little more about a bit more about the reasoning process, if you would, and what the user interface is to make that evident to someone like a physician, for example. That seems very important.
Right. And so actually...
Can you repeat the question?
Okay. And so I was asked to comment more about the reasoning process and how we can expose that to the end user. And one way that we're doing this is actually by creating something we call an evidence profile. And the way that the system works is it has a wide variety of analytics that explore a number of different aspects of the problem. And so if you take doing a diagnosis problem, a patient comes in with their symptoms, but they also have a family history, they have their own electronic medical record, there might be demographic issues related to that. All of these different kinds of information are analyzed in different ways. And then when we look at all the possible diagnoses, we can score the strength along each of these dimensions for each of those diagnoses. So you can see why Lyme disease is preferred, because it turns out the patient is from Connecticut, over arthritis, even though there's a family history of achy joints. And then you get a visualization of what's going on there. But then you can drill down into one of those dimensions and see the underlying data, whether it's documents or elements from the record.
Thank you very much.